Welcome to a deep time journey into Earth's tectonic evolution. In this video, we share insights from our paper, Plate, Tectonics Through Earth's History, Constraints from the Thermal Evolution of Earth's Upper Mantle, published in the International Geology Review. This study is authored by Sarbajit Das, EVSSK Babu, Jerome Gan, and Soumyajit Mukherjee. We examine how Earth's upper mantle cooled over time, and how that thermal evolution shaped the way plate tectonics has operated since the Hadean. A central focus of our study is the mantle potential temperature, or TP, a parameter that captures the thermal state of the mantle. TP traditionally refers to the temperature of the mantle at surface if it ascends adiabatically without melting. It gives us a consistent reference point for comparing mantle temperatures across different geological eras. This concept, introduced by Mackenzie and Bickel in 1988, has become essential in reconstructing the mantle's role in tectonic evolution and lithospheric behavior. Since the compositions of basaltic magmas change with variations in mantle thermal conditions, examining these magmas enables effective constraint and tracking of a planet's thermal evolution. To estimate TP, we use the fractionate PT thermobarometer developed by Lee et al. 2009, which reconstructs the primary melt composition of basalts that have undergone only olivine fractionation using a batch melting model. Our starting point was a global compilation of 1,214 basaltic samples, covering 1,146 Archean and 68 Proterozoic cases. The basaltic samples were from key Archean as well as Proterozoic greenstone belts, such as Greenland, Superior, Wyoming, Pilbara, Barberton, Darwar, Yilgarn, Baltic, Flin Flon, and Cape Smyth, etc. We applied a rigorous multi-stage filtering process for the input basalts. We included only samples with greater than 9.5 weight percent magnesium oxide to avoid clinopyroxene or plagioclase fractionation processes. SiO2 content had to fall within 43 to 52 weight percent, as per the total alkali silica classification. Samples required a total major oxide sum of greater than or equal to 97 weight percent. Using FC3MS and FCKANTMS proxies, we removed samples suspected of having proxenite-derived melts. We further excluded samples with evidence of clinopyroxene fractionation or accumulation at higher pressure conditions using the magnesium oxide versus CaO relationship. After applying these constraints, we were left with 101 high-quality peridotite-derived non-arc basalt samples, ideal for reconstructing mantle temperatures unaffected by local anomalies or arc-related processes. To calculate the primary magma composition and TP, we assumed an olivine magnesium number of 0.92 and a redox condition of Phi plus 3 over Phi total equals 0.1 at the source. Our results reveal that during the Archean, mantle TP ranged from 1,444 to 1,639 degrees Celsius, with a mean value of 1,549 degrees Celsius, approximately 200 degrees Celsius higher than today. Our result is an excellent agreement with an average TP of 1,550 degrees Celsius, originally estimated by Hertzberg et al. 2010, using Primelt 2 from 14 Archean age basaltic samples. This drops slightly to 1,530 degrees Celsius using Primelt 3 by Hertzberg and Asimo 2015 on that same database. A critical clarification is that the high TP values we observe do not reflect mantle plumes. Unlike plume-derived magmas, like komatiites, the basalts we used originate from the ambient convecting mantle. The TP values obtained from these basalts fall within plus minus 100 degrees Celsius of the present-day secular cooling trend, governed by an Urey ratio of 0.38, a strong indicator of ambient mantle conditions. This distinction challenges the frequent assumption that Archean greenstone basalts are plume-related. Instead, we argue they represent widespread planet-scale mantle melting, not isolated hotspots. Unlike several petrological and model-based TP estimates that suggest a comparatively cooler Archean ambient mantle, typically proposing a decline from around 1520 to 1400 degrees Celsius at 4,000 million years ago to present-day values of 1350 to 1300 degrees Celsius. Our study supports a hotter Archean mantle, in agreement with the findings of Hertzberg et al. 2010 and Koranaga 2008. We further use the calculated mantle potential temperature values to evaluate the nature of plate tectonics on early Earth. Notably, our results highlight that elevated mantle temperatures did not equate to rapid tectonic activity. Instead, they point to a seemingly paradoxical situation: sluggish subduction during the early Archean, even under conditions of higher TP. This is because a higher TP leads to extensive decompression melting, which in turn generates a thick oceanic crust and a correspondingly thick residual lithospheric mantle. The residual mantle, being dehydrated and compositionally refractory, undergoes dehydration stiffening, significantly increasing the mechanical strength of the oceanic lithosphere. Additionally, the density of the oceanic crust is directly influenced by TP. For example, higher TP results in a denser crust. Consequently, the Archean oceanic crust was likely much denser and more negatively buoyant than its modern counterpart. Moreover, with most water stored at the surface, forming a global ocean, the Archean mantle was relatively dry and thus resisted rapid recycling, resulting in shallow angle sluggish subduction and wide slab curvatures. In contrast to the Archean, the Hadean mantle was likely chemically stratified, which would have resulted in the formation of a thinner oceanic crust, see even under conditions of high TP. The Hadean mantle was likely highly convective and low in viscosity, promoting thermal and mechanical instabilities capable of eroding and weakening the lithosphere. As a result, frequent slab breakoffs and short-lived subduction episodes, recurring over timescales of a few million years, may have characterized the style of plate tectonics during the Hadean. As Earth continued to cool through the Meso to Neo-Archean, the mantle's heat output dropped, and so did the thickness of newly formed oceanic lithosphere. This thinner lithosphere was less buoyant and more prone to steep angle subduction. This shift marks the beginning of modern-style plate tectonics, with well-defined subduction zones, arc magmatism, and eventually the formation of continental nuclei and stable cratons. By the Neoproterozoic, Earth had largely adopted the tectonic style we recognize today: cold, deep subduction beneath rigid plates. We also reviewed vertical tectonic models, for example, stagnant lid, heat pipe, and sagduction in the context of Earth's thermal evolution. Although it may sound simplistic to state, the physical conditions on early Earth were likely not favorable for the operation of any of these vertical tectonic regimes. The stagnant lid model is challenged by the fact that a mixed heated mantle with substantial basal heat flux would have produced enough convective stress to overcome lithospheric strength, promoting mobility. The heat pipe model predicts an implausibly low geothermal gradient for the Hadean and early Archean lithosphere. Although more widely considered than the other two, the subduction model also has major limitations. It assumes a uniform, overly thick oceanic crust and fails to reconcile with the compositional layering, pressure requirements, and felsic crust volumes inferred during the Archean. We further conducted a comprehensive review of geological records from the Hadean to the Proterozoic, which indicates that plate tectonics has operated in some form throughout Earth's history. Ophiolites, retrograded eclogites, and paired metamorphic belts reflect tectonic activity from the Neo-Archean to the Paleoproterozoic. In the Archean, TTGs, Sanucitoids, arc-related granitoids, eclogite xenoliths, and mantle-based crustal growth models further support ongoing plate tectonic processes. Hadean zircons, with isotopic evidence of crustal recycling, suggest subduction-like mechanisms were active as early as 4.4 billion years ago. Collectively, these observations imply that plate tectonics has been a continuous but evolving geodynamic system, adapting to Earth's changing thermal state. The temporal distribution of specific tectonic features may reflect either secular variation or preservation bias. Thus, instead of asking when plate tectonics began, a more pertinent question is, was there ever a time when it was not operating? From rapid dynamics in the Hadean to transitional behavior in the Archean, and the emergence of modern-style plate tectonics in the Neo-Proterozoic, Earth's lithosphere has remained tectonically active since its earliest history. To explore our findings in detail, read the full article in International Geology Review by scanning the QR code on the screen. We hope this work encourages further research into Earth's deep-time geodynamics, the origin and evolution of plate tectonics, and their implications for planetary habitability, crustal development, and resource formation. Thank you for watching.